Okay, going live on Periscope to continue the code that I was doing yesterday with you. We were talking about Mychelium Blockchain, and so we're having session live for coding with you, coding with Michel. I'm Michel comes from Switzerland and working with Gradual Quanta to bring you blockchain tools for social change and all humanity improvement. Okay, so what we saw yesterday is the blockchain, the Mychelium blockchain is a way of making everything a block and then tracking it and then having the powerful feature of blockchain as known as it's like a database that is distributed and that is secure. So it's a peer-to-peer database, so we don't rely on any third party. So it gives us, some tremendous advantage compared to classical solutions. So let's go and start the code. So yesterday we had a version of trees, and we had the function that was called what was the name exactly? CCA, the closest common ancestors. So it's a way of there's a typo here. It's a way of merging blocks. So everybody can have their own chain of document, like any document is a block within a blockchain. And so they can have their own chain, their own view that might differ, that might not be exactly the same. And so you need to find, we need to have a way of merging chains so that we can come up with some agreement between two blockchains. So if it's financial transaction, then you have an agreement that the balance of each accounts are properly set. So how do we do that? So every modification of document of a block will create a new version. And so once we have, so it's like we have two trees of versions, and we have two branch. We want to merge two branch. It's exactly like for the people that knows the Git system. It's the same thing than the Git merge, but on blockchains level. And so what we have to do is to be able to merge two documents that are different, coming from two different authors or editors. We have to find the closest ancestors. What does that mean is that the files that has been common with the two, that has been the source of the two branches. So that is like the branching point, the fork. So we have to go back to the fork and then apply all the changes that has been applied to this source document and from both branches. And so that's a way of merging all the modification so that we have an up-to-date document that take into consideration both versions, both branch modifications. Okay, so yesterday we did the CCA function, which takes a graph, like the graph that is shown in the picture. The graph as an input, and then two nodes that are the one that we want to merge. So we want to merge, for instance, the document 3, version 3, 1A, with the document that is under the label merge, which is the 4B document. And so how do we do that? We get all the ancestors of the node A. So that in that case, that would be the document 3, 1A. And we get all the ancestors of the node B. That would be all the ancestors below, all the nodes below the document 4B. And so once we did that, so to be able to, so that's both branches, so that will be the blue the blue one for the B ancestors and the red one for the A ancestors. And so that's why we color. We color the A ancestors in red, we color the B ancestors with blue. And so we just define like we have to have a marking or a coloring graph coloring function that will take all the nodes from the ancestors A and then put the color 1. Let's say 1 is red, and for the same for the ancestors of node B, where I put color 2. And so, and also if they have a color, if there is an overlap of color, I define a color purple, which is 3, to color the nodes that will be common on both set. And so for each node that are purple, then I will increment the parents of that node with 1. So it's like I store a counter in each node, and then if I increment the parents of each purple nodes of 1, then the nodes that will have the counter set to zeros will be the closest ancestors. So that means we need to, so we wrote that yesterday, and we need now to get the function get ancestors to get, so that means getting all the previous nodes from a given node within the tree. And so how do we do that? We just go through the parents node, and then we add all the parents that we see. So the parents first, then the grandparents, and the grand-grandparents, and so on. So it's pretty straightforward. We have to be careful that when there is branch, like you can have a node that has 2 parents. So it's when there is a merge, not a branch. If there was a previous merge, then we might have a node that has 2 parents, but then we just go through all the nodes. I mean, it's not a problem if it's replicated, then we can do that later on. We can probably uniquify the list if necessary. So the get ancestor get the graph as an input and get the node that we want to look the parents from. And so we can define probably a table ancestors. And what we will do is get the parents of the node n. The parents of the node n will be like the parents, and so it's from the graph, and the parents of the graph the parents of node n is accessed with that, and that's pointer. So if it's a pointer on an array, then we have to cast it to get an array from it. Then what we should, well, let me print that just in case to verify. So printf parents s/n, and we do print the array, the parents array. So we will join and parents. Here you go. Then what we need to do is we need to push that into the resulting ancestor array before recursively calling the get ancestors on the parents. So we push that, and then we do for each of the parents we do the same. So that would be for each my parents, my p, into the array parents. And so what do? We have to let's see, in the graph, if there is no parents, then we stop. So that means we have to test if the parents exist. So parents is in an array, so we can test if there is at least one element. That will do the thing. We don't need to know. And so if there is more than one, and so we can test it with the parents if the parents, so the grandparents exist. So if the first grandparent exists, the first grandparent will be the one that is indexed by 0. And so if the grandparent exists, then get ancestors with the same, within the same graph, but at the node parents, and that we want to store it into the results. So we store it, we want to append it. Ancestors push, so we push this into the result array. So here you go, so parents, bam, bam, bam. Then that's it. Then we just can return the ancestors. Ancestors. There you go. Okay, now we have to do the other function, which is marking, the marking function. So how we do the marking function? Well, what we can do is so it takes from argument the attribute. So we keep a hash table with all the nodes attributes. Shift. Then what else? We have the nodes. So we mark a list of nodes, so we can take store the list into a point here, and we want to, here you go. So that means we set all the attributes of the node n. And what are the things we return? We return the full graph. Well, we don't have the graph even. So probably we don't return the graph. What we should return, I don't know. We don't need, I mean, because we don't need to know the dependency in the link to put the colors. Okay, so let's don't return anything. Okay, so here's the mark. Then what we need is to get the get node function. So it's the function that we get the node of a certain color, certain attribute, and that type of thing. Oh, if we want to have color, additive color, then we need to add up the colors. And so instead of equals, we can make plus equals. And so that would be like if you add red and blue, you will have purples. So for the additive color thing. And okay, let's do the get node. Alors, the get node get an attribute and the color we want. And so the attribute graph hash. So do the same. My attribute equals shift, and my request equals yes, shift again, and here same thing, meaning we have to look through every keys. We can store my results. Let's put an array. No, maybe in an array. Results here. So for each key into request, if attribute, well, we have to look for every node also. Donc for each node into keys of attribute, attribute of nodes. So if attribute of nodes, and for the keys, for nodes keys equals request keys. Okay, so if it's equal, so we should do, yeah, I don't know if we do string equals or numerical. I think numerical is okay because we for the colors is fine. So if there is a match, then we push the node into the result. So push result node. Node. My keyboard. So we do that for every request. So every key value in the request, and we do that for every node. Okay, and then we simply return the results. There you go. So we have the mark function and the get function. What else do we need? I think we okay. So I will interrupt the video here so that we can do I can prepare a test case and I will do a next video with a test case. Sorry. So that we test this program. Oh, get ancestors here, another get ancestors here. Oh, singular, so it's not exactly the same. Get ancestors. Oui, c'est bon. It's okay. Oh, there is two load. Oh, there's a copy thing. Well, there's three. Oh man. I don't know, I probably did copy paste by accident. Okay, so let's try that, run that on the shell, and so we'll restart the video once I got the test case to show you how it works. Thank you so much, and have a nice day.